Se ele quiser ficar ali, mas ele vai ter que passar também para uma...
It's not clean and bottom.
Aí ele botou o microfone na frente do ouvido e sai por ali.
I would not use it. No, I think
Because we are recording.
Yeah.
Then in that case,
Yeah,
I
you-
move a lot.
Yeah,
Não, ele pode usar esse aqui também, é só tirar, só soltar, tanto faz, tá?
não, porque ele vai usar depois para na hora do vídeo.
Ah, tá.
Então, ali ele já quer deixar posicionado.
Tá ótimo, perfeito.
Hello. So, good morning, everybody. Let's start the session today. I'm my pleasure to introduce Ernesto Estrada. He's full professor and chair of complexity science at University of Strathclyde in Glasgow, and holder of the Wolfson Research Award in the Royal Society of London, chair of the Mathematics University of Strathclyde. So he will make his talk spatial efficiency in complex networks. Thank you.
Okay, so muito obrigado. Muito obrigado.
Not done, okay, don't worry.
Okay, no, it doesn't work? It work? Okay. So then thank you very much indeed for the kind invitation. I'm going to speak in English, not in Portuguese, because the microphone doesn't understand my Portuguese. So, so I want to thank the organizer for the invitation to come here to Rio and for all the trouble and organizing my trip. And I apologize because I was planning to talk yesterday morning, but my flight was delayed, and then I just arrived yesterday in the afternoon. So I'm going to talk about spatial complexity of complex networks, and you will be surprised about that because I'm not going to talk only about networks which are embedded into geographical spaces. So I am a mathematician, so the goal of a mathematician, or my goal as a mathematician, is to measure what is measurable and make measurable what is not so. So the idea here is trying to convince you that the spatial efficiency is a fundamental multifactorial property of networks, and that we can quantify that, and that we should quantify that. So my talk is mainly directed to young researcher here that can continue and push forward this idea. So I will start here with a video, and
From the suburbs in the morning. The city is packed. But if a bold engineering proposal by Japan's Shimizu Corporation becomes a reality, there may be some surprising new real estate right in the middle of Tokyo Bay. In this, the mega city pyramid. Its shape is familiar, but this pyramid is unlike anything else on Earth. Because it's not a building. It's a revolutionary urban environment that squeezes 24 80-story skyscrapers into a three-dimensional frame. Its footprint would cover an area the size of 275 city blocks. To let the equivalent amount of land would cost more than $10 billion a year. But the walls of this massive structure are these, the megatrusses. These are the bones of the circulatory system of the living city. And they contain the critical transportation system. Hundreds of thousands of people on the move. A network linked by 140 kilometers of horizontal and diagonal aerial tunnels, meeting at 55 transfer points called nodes. It's not much smaller than an average city transit system, but it's squeezed into an area just 1/50th of the size. A complete, self-contained, self-sufficient city with homes, businesses, parks, everything anyone could ever need. If built, it will be the largest structure on Earth.
So, as you have seen here, we have a necessity for going from 2 dimensions to higher dimensions. So, growing cities in the way that we are using today is very expensive, it's very challenging for the environment, and it's also a big problem from infrastructural perspective. So, this plan goes in the idea of increasing the spatial efficiency. So instead of continue growing in 2 dimensions in a planar kind of network, we need to go for higher dimension, in this case for a 3-dimensional non-planar kind of graph. And this is one example that I can show you about the necessity of quantifying how efficiently a network uses the space in which they are embedded, but not necessarily for those networks which are embedded into geographical spaces like a city, but also for any network, because we have proof analytically that any network can be embedded into one Euclidean space corresponding to spheres in higher dimensional spaces. So, what is spatial efficiency according to the literature? So this concept comes from economical science, and it refers to the organization of the commodities or the arrangements of products or arrangements of institutions in order to guarantee more efficient time, effort, and cost. Like we have seen in the video, so there is a necessity of going out from the 2-dimensional space, because otherwise the cost would be very, very high. But also the efficiency in transportation will be increased if we change this spatial efficiency. So here, for instance, we can say that spatial efficiency refers to the organization of physical assets such as building, infrastructure, green space, which structure the transportation, communication, public services, and energy needs of business and residents within the region and beyond. So this, of course, refers to something which is embedded into a geographical space. So how now can we make an abstraction of this concept and generalize to any kind of network? So first, we can see what are the ingredients that conform what is the spatial efficiency. So the first one can be immediately learned from the video, and it means that we can go from planar graphs to non-planar graphs. I don't know if you know what is a planar graph, a planar network. So a planar network is just a network that you can draw into a plane without crossing any two edges. So there is a very nice theorem by Kuratowski that proved that a graph or a network is planar if and only if there is no subgraph which is homeomorphic to the complete graph of 5 nodes or the bipartite complete graph of 3 and 3 nodes. So here, and there is enough evidence in the literature that from the perspective of a network, most of the cities are planar. So you can think about that there are tunnels, that there are bridges, but if you draw these in a way like this, there are no crossing between the edges and the network is planar. So on the other hand, if we go to higher dimensions like the planet in the Tokyo Bay, so now you can see that you have K5 here. So these are octahedrons here. And then you have a subgraph, which is the complete subgraph of 5 nodes. So these kind of networks are not planar. So going out from 2 dimensions to higher dimensions necessarily implies, well, not necessarily, but in some cases imply that you are going from planar to non-planar networks. So you can learn as well from nature, and nature tried to pack and fold many objects in order to guarantee more spatial efficiency. So if you try to put DNA or a protein inside a cell and you don't fold these, so the length of this DNA or this protein is longer than the size of the cell. So you need to fold. This is one of the reasons. The other reasons are more physical. So you need to protect all the amino acids which are hydrophobic here into the core of the protein. And then there has been a lot of speculation about how folded and how packed the protein in general is. But what is true is that if you see a protein like that in nature, something is wrong. So probably your experimental method for crystallizing the protein has been making some mistakes. So in general, all the protein form 3-dimensional structures which are very folded and very packed. So in terms of network, we are talking that this is a path-like network or graph. So here that we have is a network that looks like a path of n nodes, and this is denoted here by Pn. And this kind of networks has a lot of interaction between not necessarily connected amino acids, so non-covalent kind of interactions, and this kind of structure looks like a complete graph of the type Kn. So there is another more subtle kind of ingredient here, and it's the bridgeness. So if you see here, for instance, this kind of graph has a bridge here, and this bridge avoid certain kind of packings of these structures. So if we represent the nodes here by penny, there is a very famous problem in mathematics, which is the optimal penny packing, and this has been solved for 2 dimensions. It's still open for 3 dimensions. And in this case, the bridge avoid to have the optimal penny packing, which is 1 penny surrounded by 6 others. So every time that you have a bridge like this, you are not allowed to make the optimal packing. So bridgeness is also one of the ingredients in this particular spatial efficiency. So then we can make a definition based on what is read in the literature about what we think is the spatial efficiency of a network. So we can transform these spatial or geometrical concept to something which is more manageable in terms of a network. And we can say that the spatial efficiency refers to the efficiency and the communication. So we are changing the language from geometry to something that we can manage in a better way, so communication. So then we need to define what is the communication efficiency in a network. And then we can think about that the main objective of communication is to maximize the amount of information which is transferred from one node to another node and minimizing the amount of information which is lost in this transmission. So then we can define this communication efficiency as the ratio of the successful information transferred from one node to another by divided by the amount of information which is frustrated, that I sent you information and it's lost. And this happens many times when you try to email somebody and after a couple of days, you realize that the information was lost. So Then we have a way to quantify communication efficiency, and by using this communication efficiency, we can infer what the spatial efficiency of a network is. So let's go to see what can we learn from the classics. So everybody here knows the classical Milgram experiment of 1967, in which a few people from the central part of United States were, you know what the United States is? It's a country, North Mexico. So a group of people here in the central part of United States were asked to send a letter, giving a letter to somebody that they know personally, and the target was somebody that was in the Boston area. So this was separated by about 2,000 kilometers. And the goal here was to see how many steps these letters take in order to arrive from the target to the destination. So the results obtained by Milgram are very well known, and the basis of the small world comes at 6 degrees of separation, etc. So if you see here the histogram of the number of complete chains, so this word here, complete, is very important, because not all the chains were complete. So they quantify only, of course, those chains that were complete. And this peak at 6, and this is the famous result that gives rise to the myth of the 6 degrees of separation and the small world concept. So here, this histogram, because of this word complete here, accounts for the successful transfer of information between the sender and the target. So these are every time that somebody gives the letter to somebody and the letter arrived to the destination. These are the ones which are accounted. So these are the successful transfer of information. But then there is this other part of the result of Milgram, which is related to the social transitivity. So if I am a friend of him and a friend of Jesus, so there is a high probability that they two close a triangle, because I will introduce they two in a party or in a meeting or whatever. So there is a high transitivity in the social relations. And this is very well known and well documented. It's quantified by the clustering coefficient introduced by Duncan and Steven Strogat. And, but there is something that we need to learn here. And it's something that happened. It has to be with these complete chains here. So suppose you are the originator of the letter. So you send the letter to this friend of you. The only thing that this friend of you know is that you were the originator of this letter. So he or she sent the letter to this guy here. And the only information that this guy has is that the letter was originated into here, because there is no memory in the communication. So what happened is that by the transitivity of the relation, with high probability, this guy will return the letter to this lady, to you. So if you repeat the experiment and you do this, after a while you are frustrated and this letter finished in the rubbish or the trash bin. So it means that you throw away the letter, and that's why not all the chains were completed. So we can think about that the transitivity accounts for part of the information which is lost in the transmission between two nodes in the network. So now, if you are the target of this experiment and you are, as you are, a rational, intelligent being, you will think about one strategy. So what is the strategy that you can think about? Well, the first problem is that you don't know the structure of the network. So you don't know what is the structure of the social network of the United States. Even you probably don't know the structure of the social network in your department. Then you have to try to figure out what kind of a strategy you can give. So you have many friends, and not all your friends are so popular as one or two of your friends. So you know that probably Jesus or any other here has a lot of friends. So there is a high probability that the shortest path goes through the highest degree nodes in the network, the most connected nodes in the network. So if everybody followed this strategy, and this is very intuitive, because you will never give the letter to me. This guy is a mathematician, is very shy. He don't know anybody, has no social relations. So why I will give the letter to him? So that's completely illogical. So, but if you give to Alessandro, he is a very popular man here in Brazil. He even knows the president, etc. So he can immediately manage to give the letter to the destination. If everybody do that, there is a high chance that the letter arrived to the destination. And if you see here in this example, if this node gives the letter to the highest degree node of its accountant, and the same do this, so you go with high probability to the destination. So sending the information to the most connected nodes or hubs of the network will increase the chances of visiting or traveling from one node to the other by using the shortest path. But we are forgetting one ingredient here. We are forgetting the transitivity. What happened is that the highest degree nodes are also the ones with the highest clustering, are the ones with the higher number of transitive relations. So given then the letter also increase the chance that the letter is lost due to the transitivity. And then we have a paradox here. We have the paradox that giving the letter to the most connected nodes increase the chances that it arrived to the destination by using the shortest path, but at the same time increase the chance that the letter is lost due to the transitivity. So then we can try to figure out why these letters arrive or why information flow in the networks so efficiently if this paradox exists. And the only way that we have to solve this paradox or apparent paradox is by considering that information is not only flowing by the shortest path, but the information is flowing by using any of the potential routes that exist in the network. If there were only necessity for shortest path, all the complex network were trees without cycles, because there is no redundancy. And then in the trees, any way for going from A to B is by using the shortest path. There is no other way. But there are no trees in real world. And then there is a lot of cycles there. So potentially because of the necessity of going by using not necessarily the shortest path, but all the available routes. Of course, before you be scandalized by this concept, I want to say that we continue giving more importance to the shortest path than to longer walks. So if you are going from Mexico City to Rio de Janeiro, so probably you go directly like I did by flying from one place to the other because Alessandro was in charge of buying my ticket. If I did by myself, probably I will go to Boston and then from Boston to Glasgow, Glasgow to Paris, and Paris to here. But this is stupid because you are not using the shortest path. So you use this non-shortest path only when there are no tickets for this one. So you give a ranking of preferences in the way that you select the routes for the network. But now by using these, we can define something that we call the communicability that was introduced in 2008. You can find many references for this in the literature. So the communicability between two nodes in a network is defined as a function of the total number of routes connecting them, giving more importance to the shorter than to the longer ones. We only need now to define what we understand by routes. And then you need to take advantage of things that you can quantify mathematically. And then we can quantify what a walk is in a network. Don't confuse walks and path. So in Spanish, we have a problem because we have only one word for both things. But here in English, we use path when there is no repetition between the nodes and edges, and walks when the repetitions between nodes and edges are allowed. So you can do backtracking. So you can go from your work to the supermarket, you forget something at home, you return home, and then go work. So you can do backtracking many times. But every time that you do backtracking, you increase the length of this walk, and then by certain kind of penalization, you are decreasing the importance of this walk. So we can mathematically represent the communicability between the nodes P and Q by the total sum of the number of walks in L steps from P to Q, from L equal to 0, which means that you stay at home doing nothing, to infinite, that means that you are wandering around the network without arriving only at the infinite time limit to the destination. But we need these coefficients here. These coefficients are necessary because of two reasons. The first one is that we need that this series converge. Otherwise, we obtain infinite all the time because the total number of walks of infinite length is infinite. So we need this series to be convergent, and also we need to give more weight to the shortest than to the longer walks, which is one of our priorities here. So let me say that we rank the eigenvalues of the adjacency metric in non-decreasing order, and we designate by the eigenvector associated with the corresponding lambda j eigenvalue. So now we can use a theorem by Frank Harari of the 1967 that prove that the number of walks of L length between the nodes P and Q is given by the PQ entry of the Lth power of the adjacency metric. This is one of the exercises I put to my students, so it's very simple by induction to prove this. So, but now by the spectral decomposition of the adjacency metric, I can represent the communicability in terms of the eigenvalues and eigenvector of the adjacency metric, and we only need to define these coefficients. So there are many ways of defining this coefficient, and you can see this in the SciAm review paper, and oh, sorry, this is 2010. So not 2014, sorry about that. Never copy and paste. So if we select the factorial penalization of the walks, so it means that for a walk of length 0, you don't make any penalization. You don't make any penalization for a walk of length 1, but for a walk of length 2, you penalize by 1/2. For a walk of length 3, like walking around a triangle, you penalize by 1/6. And for a walk of length 4, you penalize by 1/24. So imagine that a walk of length 100 is penalized by 1 over the factorial of 100. Try in your calculator to compute factorial of 100, and you will see it's a huge, huge number. So practically the contribution of longer walks is nil. So there is no contribution at all. But this is important because this makes this series convergent, and this converge to a metric function, or if you are working with operators, you can say that this is a new operator, which is the exponential of the adjacency metric. Of course, if you are a physicist, you immediately can see things here. You can relate these to partition function and to introduce all the machinery of statistical mechanics. So you simply consider that the network is, you have a tie binding kind of Hamiltonian, and then this Hamiltonian is just minus the adjacency metric. So the time evolution operator is related to this, and then the thermal Green function is given by the trace of the exponential of beta, the adjacency metric, in which beta is the inverse temperature. So you can play with these a lot, but we are keeping things simple here, and we can make this representation by using the product of the corresponding eigenvectors and the exponential of the eigenvalues. So now let's go back to communication. So we need to consider here that two nodes, P and Q, so you that were the one of the members of the experiment that received the letter, and the guy who is the target. So, but in this case, there is a communication between both. So I am trying to communicate with you, you are trying to communicate with me, because we are considering that the network is undirected. So in this case, we know that the term GPP represents or quantify the amount of information that departs from the node P, wander around the network, and return to the node P. So this is the case in which the node P send the letter, give the letter to you, you give the letter to him, and he returned the letter to me. I repeat the experiment and the letter arrives again to me. So the letter is not arriving to the destination. So this quantify the amount of information which is frustrated in the transmission of information. However, GPQ represent the amount of information that depart from the node P, and after wandering around, and you don't worry about how this is wandering around the network, arrive to the destination, which is the node Q. So we have here the two ingredients for the communication quality. So the amount of information which is lost and the amount of information which is successful. So communication efficiency is trying to minimize the lost information and trying to maximize the successful information. Remember that communication efficiency was defined previously as the ratio of these two things. So we can define this parameter here as the amount of successful information, and then, of course, if you multiply GPQ times GQP, we are assuming that the transmission is the same because the network is undirected, and then here the amount of information which is frustrated for the node P, and the amount of information which is frustrated for the node Q. If you take the square root of this, you obtain this parameter here. Of course, you can make other kind of definition, but you will see the convenience of this. And the convenience of this is that, of course, this is successful information and lost information, is that we can, that this function is the cosine of an Euclidean angle between the two nodes which are embedded into high dimensional space, particularly high dimensional sphere. So this function is the cosine of the Euclidean angle spanned by the position vectors of the nodes P and Q. And these position vectors are the position vector in this hyperdimensional sphere. So if we want to visualize that, these are two nodes in our network. So this is the node P and this is the node Q. Here is the position vector XP. At this point, O is a point inside this hypersphere. Don't be worried about that. And this is the position vector for the node Q. It's very easy to prove that the position vector is just the square root of the amount of information which is frustrated for the corresponding node. So you only need to define the position vector as the exponential of the diagonal metric of eigenvalues times this vector, which is defined from the eigenvectors of the adjacency metric. So this is a distance between the two nodes. This is the distance between the nodes in this high-dimensional hypersphere. And this is defined in the following way. So this is the so-called communicability distance, and it's the square root of the amount of information which is frustrated between the node P and the node Q minus 2 times the amount of information which is successful in the communication between the two nodes. So then the angle is given by the angle between these two position vectors, and is given here. Of course, if the two vectors are very collinear, it means that the communication between you and I is very collinear. So they are strengthened by the direction of the communication. However, if they are orthogonal to each other, so you are talking Japanese and I am talking Cantonese. So we are not communicating to each other. So then we are now going to see how this average communicability angle relates to the spatial efficiency. First, it was the first ingredient that we see, which is the planarity of the network. So we study here about 12,000 connected graphs with 8 nodes, and we see that the nodes with the highest average degree are those which are planar. So all planar graphs has very large values of the communicability angle, indicating that communicability angle is inversely related to the spatial efficiency as we expect. On the other hand, the graphs with the smallest communicability angle, which is given here, are those which are non-planar. So you can see, and I draw this in a way that you can see that these graphs are homeomorphic to K33, so they are non-planar. But more importantly, if you take the histogram for these graphs, we can see that the planar graphs has a smaller average value of the communicability angle than the non-planar graphs. If you try to do the same for other kind of distances or geometric parameters of networks, like for instance, the average path length, which is highly used when you assume that there is communication by using shortest path, there is a large overlap between the two. So by the way, determining whether a graph or a network is planar or not is an NP-complete problem. So it's not an easy task to determine that. So that's a very good property of this parameter. So we can prove very easily that foldedness also increase or decrease the angle, the communicability angle, and bridgeness also is related to it. So we can see, for instance, that for all the graphs containing this so-called barbell graph, this graph A has the largest value of the average communicability angle. And we can repeat this again, so we can conjecture that among all the graphs with the same number of nodes and edges, the barbell graph, which is here, has the largest communicability angle. So I was advised about the time, so let me run a little bit. So here we have that a small angle represents good spatial efficiency, and large angles, and the angles are bounded between 0 and 90 for simple non-weighted undirected graphs, okay? So if you go for signed graph or whatever, this goes from 0 to 180. But in the case we are studying, they are bounded between 0 and 90. So now we study 120 real-world networks representing biological, ecological, infrastructural, social, and technological systems. And this is the histogram that we obtain for these real-world networks. So what we can see is that there is a high polarization. Networks are very efficiently in their use of the space or very poorly efficient in the use of the space. And what we have here are, for instance, brain networks, internet, food webs, etc. here we have, as expected, cities which are very planar, power grids, but we have the surprise of proteins. Proteins are three-dimensional objects. They are embedded and packed in some way in order to guarantee efficiency in the use of the cellular space. So, for instance, in the case of proteins, we can represent all the amino acids by the nodes of the network and connecting two amino acids if they are physically interacting. This is the so-called residue kind of networks. So there is a measurement for the relative packing efficiency of a protein, which is the difference between the expected volume from an ideal three-dimensional structure of this object to the real one observed by using X-rays crystallography. And it's very difficult to quantify the expected volume of the protein from the ideal three-dimensional structure. But if you do that, what you see is that there is a very nice correlation between the relative packing experimentally obtained and the average communicability angle, in which you have that the smallest angle happens for the efficiently packed proteins, and the largest angles occur for the loosely packed proteins, as you expect. See that the angle here goes only from 60 to 90. So proteins are in general not very well packed, and this is something that people know very well. They need to have cavities in order to allocate the interaction with other proteins or to have the allocation of small molecules like ligands, etc. So what happened with cities? So we can now quantify the spatial efficiency of many different cities. I'm showing here just 8. I was paid by the mayor of Barcelona, so I put Barcelona here in the first place. This is a joke. But then Rio Grande in the Rio Grande do Sul is a very efficiently packed city. This doesn't mean necessarily good cities. So for instance, if a city has absolutely no park and all the city is full of streets, there is a high efficiency in use of the space, but you probably will not want to live in a city without parks. So for instance, Oxford and Mecca has a lot of green areas, which are here, these holes that you can see. Milton Keynes was a city designed in 1966 and 67 in the UK, and it's a very greedy kind of city. So there is a lot of green areas and a lot of square blocks in the city. So then their spatial efficiency is very poor in this sense. So they use all the space available for growing that city in the place they were planning to do it. So I will just skip this part. And the interesting thing here and the challenge here is to quantify this spatial efficiency for networks which are not embedded into geographical spaces. For instance, food web. But if you read the literature, there is a lot of debate about what is the niche space, what is the ecological space of this environment. So how to quantify that? To the best of my knowledge, there is no quantitative measurement for this. So we can represent the food webs by using networks, and then we can use this measurement of spatial efficiency based on communication efficiency in order to quantify that. So we found that there is something related to this spatial efficiency maybe, which is the invasion rate. So the rate in which invaders goes to this particular scenario. So you can think in terms very intuitive. If this network is very packed, there is very small spaces for the invaders to arrive to this place. But if the network is not very well packed, there are some ecological niches there, so invader species that can invade this space more easily can go and adapt to this system. And this is more or less what this paper, 1997, by this remarkable ecologist says. So we can say that frequent invasion rate means unstable environments, according to him, and slow invasion rate means stable environment. So we can infer, or we can ask whether unstable environment means poor spatial efficiency and stable environment means good spatial efficiency. And this is what you can observe. So this is the experimental log of the invasion rate, and this is the spatial efficiency. And you can see that networks with poor spatial efficiency has a lot of invasion rate, as we can expect. So now we can introduce our network into a thermal bath. Or you can bring the network to Rio de Janeiro, which is it looks like a thermal bath of 36 degrees. And so here the inverse temperature is beta, it's just the inverse of the Boltzmann constant times the temperature. And this temperature can be considered as a way of quantifying external stresses. So you have a social network here in this department or in this conference, but it could be polarizations due to external effects. So like a change in the general policy, a revolution, or that the transaction between banks can be affected by the economical crisis, or that the protein-protein interaction in a cell can be changed by physiological conditions, etc. So this is a way, this is a metaphor in order to quantify these external effects. So what we can see is that the communicability now looks very much as the thermal green function for the network. And what happened is that when beta is equal to 0, all the weights of the network are going to 0. So this looks like a gas in a way. And the communicability is nil for all the pairs of nodes in the network. You only communicate by yourself. So this is the French Revolution scenario, if you want. And the ideal scenario is beta tending to infinite. So the temperature going down to 0, and then there is an infinite communicability between any pair of nodes in the network. But what happened is that we can modify our spatial efficiency by changing this parameter. Or we can use this parameter in order to see what happened if this external stress increase or decrease. So in this direction, so beta equal to 1 is that we have been talking about up to now. And in this case, you have a deterioration of the flow of information between the nodes. So here we have two brain networks, one for the cat cortex, visual cortex, and another for the macaque cortex here. And we assume that all the interaction between the regions in the brain are deteriorating in a similar way. So suppose that there is one disease, a stroke or whatever, and then what happened is that the spatial efficiency that was very high, because these networks are very packed to be inside a limited region of the brain, is now decreasing very large, and from values near to 0 for the angle goes to values close to 90. So we are seeing how this is a tremendous decrease in the spatial efficiency of these networks. On the other hand, we have cities here. And then we can improve the efficiency of the spatial use of these cities if we go back here, and then beta now, for instance, represent the number of lanes between in the streets of the city. So if I increase the average number of lanes in the streets, what happened is that I am using more efficiently the space, because I'm not creating new streets. I am simply doing one-way a street to a two-way or to a four-way street. And this is what you can see here. So these networks are very poorly spatially efficient with angles close to 90, but this efficiency, for instance, for Rio Grande can be increased up to values of angles equal to 20. So the conclusion is that spatial efficiency is a fundamental multifactorial property of complex networks. It is related to the average quality of communication among the nodes. We can quantify this by the ratio of the successful to the frustrated information. And I think we have provided analytical and empirical pieces of evidence which reaffirm the idea that the spatial efficiency accounts for fundamental structural characteristics of networks. So the challenge here is to increase the amount of information which can be related to this spatial efficiency, proving many other things. This is a very new concept, and I invite you to contribute to this. Before finishing, a few propaganda. I have very recently, it's still in press, will appear at the end of this month. This book, A First Course in Network Theory. This is dedicated to students. This is a book for learning from scratch network theory. And this is based on a course I have been teaching in Strathclyde for 3 years. I also taught this at Emory University in Atlanta and to the African Institute of Mathematical Science for 2 times. This is a older book, The Structure of Complex Networks. The first part of the book is related to theory, and the second part is application in many different areas. So it's more expert level kind of book. And also, since 2013, we have launched the Journal of Complex Networks, published by Oxford University Press. I'm the editor-in-chief, and some of you are members of the editorial board of this journal. So we are receiving papers in all the areas, theory and application, on network theory. So thank you very much for your attention.
Thank you. So, questions? No questions?
I had just a clarification, right? So I mean, sort of, beta was KBT. So I mean, this temperature was a measure of some amount of stress in the network, right? I understand in the case of the roads, it was sort of like increasing the directional flow in some sense, right? Could you sort of comment a bit on the neural networks? I wasn't exactly sure. And what is the exact mathematical relation between beta and the communicability or the angle?
Okay, so this is very interesting. It looks like many people when say, well, you are weighting all the edges by the same amount. This is so stupid. This is so trivial. So you are doing nothing. But the problem is that when you go to the communicability, you go to the exponential of beta, the adjacency metric. So the effects, which are linear in the weighting, are non-linear in the response, because you have the exponential of beta. So then it means, for instance, this method has been used for detecting communities. I know. Many things about communities. But the important thing is that you can see how communities evolve on their external stresses. So you can change beta, and then you can see, for instance, how communities start to disaggregate in the overlapping between them, etc., in a completely non-linear way. So it's completely unpredictable from this point of view. For instance, you can find critical values of beta for a transition between connected hyper networks, which represent all these communities, to disconnected ones, etc. So the idea here is that you make a simple weighting of the edges, and this is the analogy of putting the network into a thermal bath, because after the equilibration, you have that all the links have exactly the same weight. But then what happens is that the communicability is given by the PQ entry of the exponential of beta times the adjacency metric. So if the adjacency metric represents minus the Hamiltonian, this exponential of beta times the adjacency metric PQ could be the analogous of the exponential of minus Ti, the Hamiltonian PQ. And then what you do is the wick rotation from the imaginary time to the temperature, and this is the thermal green function. This was proof in a paper in the physics report. Yeah. Okay, so everything was so clear that, okay.
Right, so is there any relation between modularity and the efficiency of?
This is a very interesting question, and I ask this question as well. My answer is I have no clue, because simply I have not studied that. So yes, bridge is one particular case of separating communities, but very, very, let's say, extreme case. So how communities are related to spatial efficiency, my guess is that it follows the same idea. So communities in some way destroy spatial efficiency. So communities are something which are, if you have, geometrically speaking, something that can be packed, and now you separate into communities, necessarily you are unpacking this network. However, the analytical relation between modularity or any other measurement for communities and spatial efficiency is not studied. So my goal with this talk was to bring you more open questions like this one and solve one in order to you to be motivated to work in this or collaborate or whatever. That is a good question.
Sorry, this is about hyperbolic networks. I was wondering whether you thought of whether there are any relations here, because what you're looking at is how easily you can pack this in Euclidean space, I'd say. Or you could turn it upside down and say, well, can I change the space such that this network is optimally packed in there? And you probably know that Gromov hyperbolicity. There's also some other hyperbolicity, the Bourguignat thing. that is very hard to calculate, and growth of hyperbolicity is horrible too. So I was wondering whether this could give you a path to a statistical, a StatMech way of approaching that, and whether you thought about that or anything.
That's great. So the point here is the following. In reality, networks are abstract realizations of real world objects. So then we can make embeddings into different spaces, of course. So we prefer, by preference, to embed these networks into Euclidean spaces. And then when you do that, well, let me put it into the following way. So we didn't start by embedding the network into any space. So what we were interested in analyzing was I forget the thank you here. So so this is the communicability distance. So we asked the following question. And the following question is related to the Milgram experiment. So how on Earth you communicate in a way that if you don't know the structure of the network and you follow the strategy of following the information by the hubs of the network, and the hubs increase the chances of the shortest path communication, but also of losing the information, how we communicate so efficiently in networks. So we then defined the communicability distance that was previously defined. So let me give you one example here. So you are trying to communicate between P and Q, and this is the structure of your network. So this P is a node, this is Q is a node, and then you have this cluster here, and you have this detour from outside the city. So what happened here is that, of course, if you are trying to communicate by using the shortest path distance, you go by using this shortest path. But if you account for the communicability distance, so the communicability distance, the total distance here could be the sum of the communicability distance between these edges. So this gives you this number here. Now suppose that you say, well, let me go by using this other route here. And in this case, what you obtain is this total communicability distance. So it means that going by this route is shorter in terms of communicability distance than going by using the shortest path. Why? Because the shortest path goes through the hubs of the network. And going through the hubs of the network allows you to be lost because you don't know the structure of the network. So you go here and you have 1/3 of probability of going in this way, or this way. Suppose you go here. The only thing that you know is that you were coming here. Well, you can do either here or here. So suppose you go here. The only information that you have is that you were coming from here. So you can go in this way or this other way. So if you do in this way, you are lost. You return to the origin point and then you will be lost. So in general, the shortest communicability distance route is the shortest path that avoid the hubs. Now, this is not answering your question. The point is that when we put this forward, we discover then that this induces an embedding into a high dimensional sphere, which is Euclidean. So there is a natural correspondence between this distance defined in order to avoid this problem in communication and the embedding which is produced by it. Of course, if you are looking for another property, probably you go to the hyperbolic space. But what people have done in the case of the hyperbolic space is a priori define the embedding. So they say, okay, I will embed the network into a hyperbolic space. And I can say, yes, okay, why not? And why not in another different kind of space? Spaces with positive curvature or whatever. So then the difference is that here, the embedding arises as a consequence of the definition, not as a priori kind of definition.
Up next, it's my pleasure to introduce Jesus Gomez Cardenas from the University of Zaragoza. Jesus is a PhD in physics and he's done postdoctoral studies at several great universities. He's currently the senior researcher at Zaragoza. Sorry? No, I don't know. Can you projects, organization, academics, evolutionary dynamics, and so on and so forth. He's involved in a bunch of these, and he's also currently, very cleverly, I can tell, professor in a special grant as a visiting professor at Salvador Bahia, which is a nice place for the world to visit, so well done. And he's going to talk about urban mobility, socioeconomic status, and contagion processes. So,
Hopefully, yeah. I will take this. Yeah. The thing is that. Yeah. No. It doesn't work. Which is? Okay, thank you very much. Well, I wish to thank the organization for this invitation, and also congratulations to all the organizers and people of the staff for making possible this first edition of NetSci-X. I hope it's the first one of many others to come. Well, the title of the talk is a mix of three things. Well, urban mobility. This is something that, okay, you heard about last day, the talks by Jose Ramasco and Marta Gonzalez. So I will skip this part, or I will talk a little bit about this. Social status, that I will introduce it in the later part of the talk, and contagion processes. But let me start about talking about contagion processes. Maybe it's the most prolific area in network science, or the most studied case of dynamical processes on top of a network. There is thousands of papers since 2001, being the seminal one by Vespignani and Pastor Sartoras in Physical Review Letters in 2001, which has collected more than 3,000 citations in Google Scholar. And well, this was the first paper, and following this paper was a burst of studies coming from different disciplines, and the major disciplines devoted to epidemic spreading or contagion processes in network are computer scientists, epidemiologists, and social scientists. Okay, all of these branches, which are seemingly unrelated, took the same tools in order to study the cases of the real scenarios that took place in the last decades. And these scenarios, of course, are related to epidemic spreading, for instance, in the case of epidemiology. And okay, the case studies was how this epidemic, this disease spread across countries, across continents, and across the world. And there is a big difference in the way a disease advanced from 700 years ago, for instance, the Black Death, which took years to cover the whole continent, the whole European continent. And then nowadays cases like the H1N1 or the SIRS viruses, which took weeks in order to cover the whole world. This is obviously a consequence that today we have other opportunities to travel, other opportunities to communicate, and this favors the onset and the outbreak of pandemics. The other case of a study is the social contagion processes. In this case, we study how information, rumors, technology, ideas are adapted by the individuals, and it's obviously different the way we communicate each other and the way these ideas jump from the transmitter to the adopter because of the new communication tools we have nowadays. We are in the digital area, and we don't have to make, again, the Milgram experiments, as Ernesto said. We can use WhatsApp to communicate instantaneously with other parts of the world. And especially important is the study of the unfolding of social movements, like the Arab Spring or the Indignados movement in Spain or the Occupy Wall Street. These are all evidences that something has changed, and we have to incorporate the network perspective into the contagion processes that have been studied for decades. The thing is that the theoretical tools have not changed anymore. So, I mean, they are more or less the same, and they all relate in compartmental models. Compartmental models is the way we have in order to jump from the microscopic contagion processes that occur from individual to individuals to the large scale, to the macroscopic state of your network or your population or your system. And they assume that individuals are in states, okay? For instance, in the SIR model, you assume that each individual or each node, if you want, can be in one of n states at some time t. So that the states are susceptible or healthy, infected, and infectious, and recovered. Okay, so you have these three different states for each individual in your system. Obviously, there are transitions between these states, and the transitions are mediated by some rates. Okay, so if you are healthy, you are prone to catch the disease if you contact another infectious individual with some probability lambda, okay? And once you have the disease, so you are infectious, you can infect other individuals, but you can recover spontaneously with some rate mu, okay? So these two parameters, these two rates control how efficient the disease spread across the populations. And finally, the final impact of a disease, of a SIR disease in this case, is measured by a macroscopic indicator, which is the fraction of individuals that are recovered. Why? Because in an SIR epidemics like this one, the dynamics dies out when the population is composed only by healthy individuals and recovered individuals. So there is no infectious individual in the population, so the disease stops spreading. And you measure what was the success of your spread process by measure the fraction of recovered individuals you have at the end of the dynamical process. Okay, this is the SIR model, but there are many other examples like SIS, SIR. It depends on the kind of disease or on the kind of topic you are studying, the framework you want to use, okay? But the main result regarding the spreading of this kind of disease in complex network was given by Vespignani and Pastor Satoras, and was the vanishing of the epidemic threshold. Okay, so for scale-free network, heterogeneous networks, and in the thermodynamic limit, the minimum amount of infection rate that you need in order to spread the disease to a macroscopic part of the population vanishes. And this was an astonishing result that spurred a lot of studies in computer science, in epidemiology, and also in social science because of this seminal result. Okay, well, this was a naive introduction to what is epidemic spreading and what are compartmental models, because we will use the SIR model in our studies. Then let me move again to the first slide. Now let me talk how urban mobility and contagion processes has been mixed. Okay, I won't talk about urban mobility. I refer to the talks of Jose and Marta for details. I will just say a couple of slides. I will show a couple of slides about how urban mobility and contagion processes are mixed. So the answer to this is metapopulation models, okay? Why do we need metapopulation models? Because we want to add some realism to the epidemic spreading scenario or to the social contagion scenario. And we need to add the space ingredient. So now you assume that individuals are not the nodes of your network, but they live inside the network, like the workers were that Ernesto were mentioning in the last talk. So you assume that there are different populations, and populations means a part of a city or a country, okay? And there are individuals, humans, living inside this subpopulation. At each time step, what you propose is that each individual moves with some probability P from one population to a neighboring one, okay? And this movement is done according to the observations, to the empirical observations. So if you have a city and you have the city divided in different urban areas, you have measured the transitions between one urban area to another one, okay? So you take the statistics, you take this observation, which can be based on surveys or mobile data, in order to construct this network of transitions between different subpopulations. Once all the individuals have made the jumps or stay, if they decide to stay inside the subpopulation, you make the dynamical processes you are studying, in this case epidemic spreading. So you have to take into account the two parameters, lambda and mu, and then you start to infect individuals and recover infected individuals, okay, according to your epidemic process. And finally, all the individuals come back to their original subpopulation and the dynamics starts again, okay? This is the sketch of how a metapopulation framework is done in a complex network. Okay, this framework is far more difficult than the typical network perspective, okay, in which the individuals are identified with nodes, okay? And there are some theoretical aspects, mainly covered by Vespignani and Kolitsa. So there are few analytical results that can be catch within this framework. But there are a lot of applications, okay? Because we have a lot of data sets about mobility in the whole world. For instance, you can recall the transportation, the air transportation network within continents and also within the urban environments. So you can capture all this data and construct models in order to mimic, in order to make simulations about what happens when a disease outbreak happens in the world, okay? So in our case, we will take the consideration of two cities, Bogota and Medellin. Bogota and Medellin are the two major cities in Colombia. Bogota have nearly 8 million of people, and Medellin the half, 4 million of people. So there are very big populated areas inside Colombia. And say, okay, so you are going to do another study about a mobility network, okay, a real mobility network, Bogota and Medellin, and to make the simulation of the epidemic experience. But no, we will introduce a novel ingredient, which is that of social status, okay? Why? Well, Colombia is a very particular country. It's a very nice country. I recommend you to visit Colombia. I mean, I'm completely in love with it. But is the most unequal country in the world, okay? In the world, we know, okay? So we have data about the incomes of the people, and we can measure how is the difference between the 20% richest of the population and the poorest 20% in the population. And what happened is that Colombia is in the top. So if you rank the countries, Colombia is the most unequal countries. Aquí you can read that in Colombia, the incomes of the top fifth are nearly 25 times those of the bottom fifth, okay? So you have a marvelous country in which you can find this. You can find a cities which resembles those in Europe or States, and you can find in the same city these kind of constructions which are completely legal, made because there are a lot of this, I don't know, the displaced people from the country because of wars, because of a lot of problems. So this is due to historical problems. And you have a country which is rich in what is resources, natural resources, but you find that people have not even electricity or normal water in order to live, okay? So you have find these differences in this country. And these translate into official data, okay? So you live in Colombia, you live in Bogota, you live in Medellin, and you have a number associated to you. You can be 1, you can be 2, you can be 3, you can be 4, you can be 5, or you can be 6, depending on your incomes, depending on the place you live inside the city. So from 1 to 6, from extremely poor, from strictly rich, you are always associated to a number. Of course, you can change your number. You can, okay, you can progress in your life, you can have a better job, etc. And you can go from 2 to 4, or going to 4 to 2, okay? It's impossible from going from 1 to 6. This is, of course, in a life, you cannot do this kind of change in your side. So you have this, you have these areas, Bogota and Medellin, and you see in the colors the place where people from strata 1 to strata 6 live. You see Bogota, for instance, this part, okay, the northern east part is associated to rich people, to people from strata 4, 5, and 6, while the southern part and the west part is associated to strata 1 and 2, okay? In Medellin, you have north this place and south this place. Medellin is like this, so rich people live in the south, and poor people live normally in the north part and in these outside areas, because Medellin is like a valley. It's the Aburra Valley, and all the people live in the top of the valley, okay? So there is a kind of stratification, a very big stratification. That's why these surveys, this data set about mobility are important, because we know not only the destination, the origin and destination of people, but also what status they are, okay? Or what the status they belong to. So we have this, the composition of the people in Bogota and Medellin. You can see that the strata 1, this is 1 and 1, 2 and 3 are the most populated strata, okay, followed by 1, and then you have 4, 5, and 6. And more or less is the same in Medellin. So if we go to the surveys and we disregard the mobility data for different status, and we have here the plot, the maps for status 1, 3, and 6, you can see that the mobility patterns are completely different, okay? Completely different because of different reasons. Marta told yesterday that there is a big problem for extremely poor people, and that's the point why for the status 1, people is concentrated in their living areas. That's why they cannot afford going to work. The salary they have for working, it's not enough in order to cover the expenses for going to the place of work. So they are constricted to live or to stay where they live. For the status 6, it's more or less the same, but it's the other reason. They don't need to go to work. They have enough money. They own companies, they rule a lot of things, so they don't need to mix with other people. There is also a risk in mixing with other people. And finally, you have a status 3 that more or less is the typical status we know in Europe and the States, in which, okay, they move from their house to work, etc., etc. So it's a regular pace. They cover almost all the city, the urban area. And more or less, the same happened for Medellin. You have here a status 1, as you say, in the top of the valley. And you have here the status 6. They only move. This point is the airport. Okay, this is the only displacement they make. And for a status 3, you have, okay, a very high coverage of the urban area. So the question is, what's the role of these different mobility patterns in the spreading processes? Okay, and the main ingredients are metapopulation and epidemic spreading, as I anticipated before. So we have our city divided in different urban areas. We know the patterns of mobility, so we know that what people from subpopulation I goes to subpopulation J or L. And we know this information for each strata. So we know what's the probability that a person with from strata 1 living in subpopulation I goes to subpopulation J, which can be different from a person from strata 3 living in the same subpopulation I for going to the same strata J. Okay, so we have this information. And inside each area, you have an epidemic dynamic. So you can have susceptible, infected, and recovered. So we will make use of an SIR model in order to mimic or simulate how the contagion process take place. Okay, so the contagion process that can be the contagion of a disease, the contagion of an idea, etc., etc. All the general as you want. And the main result is this one, okay? If you have an epidemic spreading scenario, you always plot the same figure, the same plot, which is the fraction of recovered individual as a function of something related to the spread of the disease. It can be lambda, but now it's fixed. Lambda is the infection rate. It can be the recovery rate, which is, in this case, is fixed. Or in this case, we decide to plot as a function of the mobility probability. So the smaller p, people stay in their subpopulation, the larger p, people tend to move across the system. And obviously, the impact of the disease grows with p, okay? As long as they start moving, the more the disease is easily to, the disease becomes easy to transmit. And the first result is that we can differentiate two classes of status. In the solid line, you see the average impact of the disease. So it's the fraction of recovered individuals regardless of their strata, okay? And the points point out the impact of the disease for each of the 6 strata you have. And you see that the status 1, 5, and 6 are below the average, while status status 1, 2, and 6, while status 3, 4, and 5 are above the average. Why? Because they mix more than the average, while status 1, 2, and 6 mix less than the average, okay? Which is something that you expect by looking directly to the maps, okay? And it's confirmed by the impact that an epidemic scenario has on each of the state. Okay. Now there is another experiment we did, which is a target initial conditions. Okay, target initial condition is okay. Normally, you start by putting a initial small fraction of infected individuals in your population. Okay, but this is done regardless of the strata. Now we put an initial small fraction of infected individuals, but only in one state. In this case, this is status 1. Okay, sorry. status 1. So we put all the infected individuals belonging to the same status, not the same place, but the same status, okay? Why? Okay, this is not realistic, but we want to see how is a hierarchy if there is, and there is. If you start with a status 1, what you see is that first, there is a very big increase in the number of infected individuals, while the rest of the population is apparently completely unaware of what is happening with this data, okay? Then this reach a maximum and start to decrease. And what you expect from normal SIR is that this decrease will slow down until 0, okay? But this is not the case. There is again a minimum, and then there is again an increase. Why? Because after some time, status 2 and 3 has been awakened by the disease and started to reproduce the disease again. So this affects, at the end, status 1. And there is another second minimum due to this second avalanche that affect status 4 and 5, which are later on, okay? There is a delay induced by the separation between socioeconomical status. So you can put these 3 stages. So these target initial conditions allow you to unveil that there is a social separation. And you can do the same for status 3 and 6. And there is always a kind of separation between social status that it's unveiled by a time separation for the onset of the epidemic in each of the states. It's also interesting in status 6 because you see that status 6 is very similar, very akin to status 1 in the sense that at the beginning, only status 6 is affected by the disease and then is followed by a sequential avalanche of disease that affects each of this data. You can do it, you can perform these numerical simulations. Okay, this is for one numerical simulation, but you can do it, you can do it many times, and average, and finally you have a matrix, okay, in which you see, okay, if I infect first status 1, what happened? Which is the time needed to start the epidemic in each data. And you see that if I start in the start epidemic in status 1, it takes a little bit to infect 2 and 3, but it takes a lot to reach status 6. Conversely, if I start epidemics in status 6, it takes more or less the same time to reach status 5, 4, 3, and 2, but it takes a lot of time to reach status 1. So the result is that this time hierarchy in the onsets, in the typical onsets, reveals the separation between the socioeconomic classes. And finally, and this is my last slide, there is another way to see that this separation, and it's to see who infects who. So now we turn to the scenario in which the initial seeds are not associated to each status. So the initial fraction of infected individuals is, rather, so it's randomly put in your population, and you can see this. You can see each node corresponds to a status 1, 2, 3, 4, 5, and 6. And if you have this line is the number of infection that status 1 causes to status 2, okay? This is the number of infections that the status 2 causes to status 3. And the important thing is this is not symmetric, okay? So status 1 causes a lot of infections in status 2, but the status 2 doesn't cause a lot of infection in the status 1, causes a lot of infection in the status 3, which in turn doesn't cause a lot of infections in status 2, cause a lot of infection in status 4. So there is a hierarchy in the infection, a hierarchy in the contagions, that is again a fingerprint of the social separation that you have in your society. Okay, so this is the main message that I want to transmit. So finally, let me thank my collaborators. This is the 2 people in Colombia, Medellin and Bogota. Obviously, they collect the data, they analyze the data, and they are very, very helpful, and they also help in the computer simulations that were led by Alessio, my former student at Zaragoza, now at Lausanne, and Sandro Meloni in Zaragoza. So finally, just to make a little propaganda as well, so don't miss that there is another NetSci conference in Zaragoza. I know you don't know where Zaragoza is. It's in Spain. It's where the next NetSci will be. The typical answer is just in the middle between Madrid and Barcelona. Go to Google Maps and you will find the place. I promise you that you will enjoy the place. It's a very nice city with a lot of cultural heritage from Muslims to Romans. I mean, and it's worth to visit. So these are the important dates, and I invite you to come. So thank you. And good wine also. Yeah. Very good wine. And food. Thank you very much.
Hi, thank you for the talk, very good talk. I wonder if your results, they are more related to the spatial stratification of people. The poor are in a place and rich are in the other place, than with the social stratification. And it's more or less a provocation and an invitation. I think that if you run your simulation in real, maybe you have different results. Yeah, because they are more mixed. So you have a very rich.
Yeah, this is a difference between Colombia and Brazil that I noticed very easily. Yeah. In Colombia, you have this compartmentalization. You see, okay, don't go to the south because it's dangerous. Here is, okay.
It's like São Paulo, more or less.
Exactly. In Rio and Salvador, for instance, Salvador is the same as in Rio. In Salvador, you find a lot of favelas spotted just close to the very rich area. Yeah. So maybe yes, maybe it's a consequence, but not the only one, because there are people from strata 2 that can afford. There is another study, I don't put the reference, about how the transportation means are covered by the population. And you see that, I have the reference here, if I'm allowed to, just not to hide it because I hide it. If I have here. So you see that because of the problem of transportation, Colombia has, or the people in Colombia, this is the dark eye. There is a lot of means of transportation. So for status 1, it's okay. They only go by food and by I don't know, by animal means. So because it's this way. But status 2 and 3 have a lot of possibilities that are only devoted to them. Okay, which are very cheap. Very, they are shared in the sense that they share a lot of public transportation, which are very small, like these ones, okay, which are very, very cheap. So they can afford to go to other places. But of course, also the spatial structure plays a key role. So I would like to have also the data sets of Rio in order to make the same study.
More question.
Yeah.
So my question is on the last slide that you showed about more or less which strata affects each other. Are those links? That one. Are they related to the absolute values on each status, or is it normalized by the size of each status?
It's normalized by the total number of contagion of the total status. Yeah.
For instance, the 6, 1 to 6, for instance, normalized.
It's normalized by the fraction of total infections in your population. In the population.
I wonder how it would change if normalized by the size of each status.
Yeah, we have also these plots. I didn't show it not to mix different normalizations because it always, but it. It's the same message, okay? There is more people in the stratus 2 and 3 than in the rest of the population, but the important thing, or the most important thing, is this one. It's a lot of infections from 1 to 2 that this brings the cascade to the other strata. And also the non-symmetric flavor of the links, which is something that for me is surprising. And the roots of this non-symmetry is the SIR problem. The problem that I can infect you, but when you are going to infect me, I'm already recovered. For sure, if this is an SIS model, which is only for infectious disease, very special type of infectious disease, like sexual transmitted, for instance, this would happen and probably it will be symmetric.
I guess my question is also related to this picture here, but it's a different one. What I'm confusing here is because when you show the number 3 distribution, it seems to percolate the entire city, right?
Mm-hmm.
So I was expecting actually to have this 3 be responsible for the infection of 6 and 1, right? Well, so
Also 2 is percolating. I didn't show the picture of 2, but 2 is also percolating. It's different the way it
right,
moves.
but why is 6 not having the same effect as 1? Because they seem to have sort of the same spatial distribution, as you said yourself, right? So 6 stays there and 1
Good
stays
question.
there, right?
Because 1 and 2 are mixed, and 6 is not mixed with anybody. I mean, 6 is not mixed with people from 4, 3, or 2. And the thing is that people from status 1 live very close with people with status 2 and 3. And these are the people responsible for the burst of the disease. Status 6 is isolated, as you can see.
But so was 1, right?
No, 1 is isolated, but in close contact. Is the mobility, the small degree of mobility they have allows them to contact people from status 2. And this causes the avalanche in the infections. Status 6, I mean, you are so rich that you don't care about what happened in the rest of the world. I mean, you only go to the airport in order to travel to Miami or to Las Vegas or whatsoever. I mean, they are totally isolated. Okay, so thank you very much.
I have some announcement. We are going to coffee break now, and then we, after coffee break, we'll start the oral sessions presentations. It's in room 9th floor and 10th floor, 921, 922, and 1014 and 1013. There was some changes in the program. We have some new versions of the tailored program outside. People who were not here today, please get this new program to see. There are some new sessions today. And after oral presentation, we'll come back here for lunch. And then in the afternoon, we have oral presentation. And I would like to ask for the people that put posters outside to take out the posters so that people of the poster session today can put their posters. Thank you very much. So.